lemma. And I apologize once again for the corrupted notes from the last time. So let me briefly recall what we did last time. In the end, I mean. We had a morphism of curves f from one curve to another, surjective, finite. Of smooth projective curves. Corresponding to an extension of fields. Rational functions on S embedded into rational functions on C. And then for a point in the base curve, we considered the corresponding pullback of the divisor. Is the sum of EC times C in the preimage. Well, set theoretic preimage of this point. So there's an effective divisor on the curve C, and those EC are called ramification indices. Of f at the point C in the curve, and we developed some technique to compute those ramification indices. In particular, if you want, what we proved last time was the following lemma, that if f is, well, say if star is a separable extension of fields, then there is an open subset U in the base curve such that f is unramified over U. That is, for any point C such that f of C lies in U, the ramification index of C is just 1. And then, in other words, they say that f is étal over U. Okay, and well, let me review briefly the proof of this lemma. So we have the non-degenerate trace pairing from K of C to K, and it's linear over the base field K of S, and it's pairing, sorry, so it's pairing to K of S, and it's important that the pairing is non-degenerate. That is equivalent to the fact that the field extension is separable. Okay, so it gives rise to the pairing at the level of regular functions. Okay, and this pairing, so let us call it B. It's bilinear form. So B is generically non-degenerate. I mean, generically, if we are allowed to use the terminology generic point, then the functions of the generic point is just the field, the field of rational functions. And on the level of field of rational functions, our pairing is non-degenerate. But what I mean that there is some actual open set U where this pairing is non-degenerate. And how to find it? Let's fix some basis of our field extension, K of C over K of S. Just choose any basis at all. And then let's write down the trace pairing in this basis. It will be given by a symmetric matrix. And now this symmetric matrix is non-degenerate, so its determinant is a non-zero constant. But by constant, I mean an element of the base field, K of S. Okay, so a non-zero element of K of S. And now this element is a rational function on S. It has some poles, it has some zeros, but at some open set U, when you throw away your poles and zeros, it is a regular invertible function. And this is our set U. Okay, so in other words, it gives rise to an isomorphism from this locally free sheaf, the direct image of regular functions on C. It's an isomorphism to the dual sheaf. Okay, so but it's only over some open U in the base S. Okay, but now it's also compatible with taking fibers. So we obtain for any point small s in our open set U, we have the fiber of this direct image at this point S, and there is an isomorphism to the dual space. But these are just finite dimensional vector space over K, over the base field K. Okay, so this B sub S is the trace form of the finite dimensional K algebra. Okay, the restriction of our sheaf of algebras to the point S, the fiber of this sheaf of algebras. Okay, but the trace form being non-degenerate is equivalent to this algebra having zero nilpotent radical. This radical being zero, and this means that this algebra is just the direct sum of field. like this. And finally, this means that the divisor the pullback of our base point S has all multiplicities. One. Okay. So if C equals 1 for any C in the satiric preimage of this base point, and so we say that F is unramified, or else total over U. Okay, and now this lemma is proved, and let us also derive some differential formula for the ramification indices. Okay, so let us choose a uniformizer pi in the maximal ideal of the local ring in the base. Sorry, in the base it's small s, and maybe let's start with the case when S is in this set U where there is no ramification, and then we know that the pullback of this parameter is a local parameter. Well, is a uniformizer at any point C in the satiric preimage of S. Yeah, because the ramification index is 1, and it means that at the level of differentials, the pullback of differential d pi of this uniformizer is the same as differential of the uniformizer at the curve C. Okay, and this non-zero. Yeah, because it's uniformized. Fine, and this means that globally the well, how to say, dual differential, the pullback from the one forms on the base curve to the one forms on the C curve is non-zero.
Извините, а какое мы свойство использовали для доказательства коммутативности F со звездой D? Свойство uniformizer.
I mean, this commutativity of F star and D is the basic property of differential, naturality of differential. Okay, this was proved a long time ago, in the beginning of January. But now we see that it's non-zero, and it means that that globally there's an isomorphism of sheaves. Okay, these are just invertible sheaves, locally free rank 1 sheaves.
Спасибо.
Thank you. It's over U. Okay, and hence over the whole of C, we have an exact sequence. 0 goes to the pullback of one forms on S. goes to one form is on C, and there's necessarily an embedding of sheaves in invertible sheaves, but there might be something in the quotient, and what you have in the quotient, just by definition, is called the relative one forms. Okay, so this is just definition by construction.
Вы же написали, что они изоморфны, эти два пучка f со звездой
They're
s.
isomorphic over this open set U, right? But not over the whole curve C. I mean, this pullback differential may have zeros away from U. Okay, so the fiber of this map. Okay, on the fibers over U, it is an isomorphism, but away from U, it can have zeros on the fibers. Okay, so this means that this embedding of sheaves can have torsion quotient sheaf. Okay, or by definition.
Again, why is this an embedding?
Pardon me? Why is it embedding? Because one morphism from an invertible sheaf, I mean, a morphism from one invertible sheaf to another invertible sheaf is either zero or an embedding. Yeah, what else can happen? They are both embedded into the big quasi-coherent constant sheaves of rational sections, right? And these are just one-dimensional vector space over this field of rational functions. So the map on the sheaves on the map from one-dimensional vector space to another one can be either zero or an isomorphism. Okay, or in particular injective. It's either zero or injective. Okay. So well, maybe let me write what I told in Word. So it's embedded into rational sections of OS. This is embedded into rational sections of OC. Okay, and this morphism is not zero, so it's an embedding, and hence d star f is also an embedding. Okay, so so by definition, the sheaf of relative differentials omega c over s is the quotient omega c over pullback of omega s, and it is a torsion sheaf supported away from the preimage of U. Okay, fine. So let me formulate the next lemma. So first of all, the sheaf of differentials on the curve C is obtained from the sheaf of differentials on the curve S pulled back to C just by twisting by the divisor associated to this torsion sheaf of relative differentials.
А что означает вот f со звездочкой от s? Это же пучок дифференциалов. Дивизор — это тоже какие-то пучки. А что означает операция скобочка?
Here, well, for a locally free sheaf F and a divisor D, there is the twisted sheaf f of d, the sheaf of sections with poles at d, so to say. Yeah, last time we said that this f tensor O C with OC of D. Okay. Last time we gave the definition.
Да, спасибо.
Okay. Okay. So this the first claim, and this is just obvious by construction. And the second claim is a little bit less obvious. We have this effective divisor, and let's write it down as ramification points with ramification indices. Okay, so well, a certain finite sum, and then the claim is that the multiplicities DC is well, they are at least the ramification indices -1. I mean, if there is no ramification, then ramification index is 1. Okay, and in fact, there is an equality here in zero characteristic. So DC is exactly EC -1 if EC is not divisible by the characteristic of our base field. In particular, if the characteristic is 0, then there's an exact formula for the multiplicities of the divisor of the relative differentials from the ramification indices. Okay, so let's prove it. So let's choose a point upstairs and a uniformizer pi at its image point in the base, and then we know that the pullback of this uniformizer is some power of.
Извините, можно спросить?
Yes.
А мы раньше вот написали в пункте Б, что вот дивизор омега равен сумме dc умножить на c, маленькая. А теперь мы говорим, что c маленькая – это точка на кривой, но это же подпучок в омеге должен быть какой-то.
First of all, in Russian you say divisor, and second, what is your complaint once again? Can you repeat your question?
c маленькая – это подпучок в омеге. А теперь мы говорим, что c – это точка на кривой.
I don't understand. Where do you have small c as a subsheaf in omega? No, I don't understand this. I don't understand what you're saying.
Мы написали, что div омега равен сумме dc умножить на c.
Yes, but well, there was last time we introduced the notion of divisor of a torsion sheaf. Maybe you should go over this notion. It is essentially the sum of points in the support with multiplicities equal to dimension of local sections. Nothing else. Yeah. So just remember the dimension of local sections of torsion sheaf. So anyway, the pullback of a uniformizer is some power of the uniformizer upstairs. So let's say that it's the uniformizer var pi to the power EC, or a uniformizer var pi at C. Okay, and now let's compute differential. We get the differential of the co-differential of d pi is just how do I say? It's EC times var pi to the differential to the power EC minus 1 times d var pi. Okay, just by Leibniz rule. Okay, and there we are. So we say that we see that it vanishes at C to the order at least EC minus 1 and exactly EC minus 1 if EC is not divisible by the characteristic of K. Okay, so this is proved, and the important terminology is that if EC is not divisible by the characteristic of K, then it's called tame ramification. And if EC is divisible by the characteristic of the base field, then it's called wild ramification. Okay. Well, I wonder if anybody of you has had some courses in number theory or arithmetic, and so maybe then you encountered this terminology. Yeah, just for the number fields or.
Yeah, I did.
Okay, yeah, you're very good. Okay, so it's geometric analog of it. So certainly everybody heard about this very fundamental analogy between numbers and functions, and this is one of the manifestations of this very important phenomenon. Okay, so this is all about separable extensions and morphisms, and now let's go to purely inseparable. So we suppose that the field extension is purely inseparable. And for the case of curves, we can explicitly construct and classify all such morphs. Explicitly, well, constructible for curves, not in higher dimensions, but for curves. Namely, they are all Frobenius morphisms. What do I mean by this? Well, we know that the degree of this extension K of S, sorry, K of C over K of S is necessarily some power of the characteristic of our field. Okay, and I will prove that for a given Q that there exists exactly one morphism like this. I mean, if you fix S S and fix Q, and then I claim that there is a unique such a morphism. And it will be called Frobenius number Q. I mean, it's like taking Q power.
Он неотделим.
Pardon me?
Почему он inseparable?
Well, but do you remember definition of being separable? The trace form.
Замкнутость в диагонали, да?
No. It's some clash of terminology. It's something absolutely different. It's from basic Galois theory, field theory.
Все, понял, спасибо.
Yeah, it's just some confusion of terminology, but nothing can be done about it. Okay, so I mean that the trace form is zero. Yeah, the trace form is just identically zero in this case. Well, we take the field of rational functions on S, and then we do have morphism. Maybe I should denote like this, to itself, that just takes, once again, it just takes any element X here to its qth power. Okay, and somehow, since we fixed the base curve S, it will be notationally convenient to think of this as an extension from K of S to K of S to the power 1 over Q. It's just a notational, it's just a notation. So these both fields are the same, are isomorphic. But it's a non-trivial embedding from the field of rational functions on S to itself. And this embedding is just taking a qth power. But once again, for the sake of notation, I view the second copy of this field as the field of qth power roots. Okay, because I want to construct so to say the covering of my curve S, and well, this will correspond to Frobenius covering of the curve S. Okay, so the Frobenius morphism from S with index Q to S, but again, they're actually isomorphic. The morphism is not identity, but the two things are isomorphic. Is the normalization of S in this field extension. Okay, so the next lemma, completely describing non-separable extensions, is as follows. So first of all, this Frobenius morphism has degree Q. Second, Frobenius morphism is a homeomorphism. Maybe you remember, I think this was an exercise in the very first home assignment. And the push forward of the structure sheaf of the covering curve is isomorphic to the sheaf of regular functions with qth roots extracted. well, and this isomorphism is just takes qth power. F goes to f to the power q. Okay, and finally, any purely inseparable morphism F. Oh, sorry, no. F is bad. Well, how should I denote a morphism? Well, maybe G from C to S of degree Q is isomorphic to what we just constructed. Okay, so let's prove this. Maybe to prove the second part first. So take a point in the base and its pre-image S prime in SQ such that the Frobenius of S prime equals S, and we want to prove that this S prime is uniquely defined. We know that it exists because any finite morphism from normalization to a curve is surjective, right? So there is such an S prime, but I want to prove that it's unique, and then we'll have a homeomorph that S prime is uniquely defined. So how do we do this? We consider the local ring in the base, and how is it obtained? If you remember from our construction of curves from fields of fractions, we take the local ring upstairs and then intersect it with the field of fractions downstairs, like this. Okay, but now we know that the local rings are all integrally closed because the curves are smooth.
Извините, а ведь локальный пучок SQ, S', он же, ну там же лежат другие функции, нежели в КС.
Absolutely, that's why I take their intersection. You see, you take the intersection, right? The local rings downstairs or the local rings upstairs intersected with the rational functions downstairs, right? In the base. So any local ring, in particular this local ring upstairs, is integrally closed, and hence we know that if you extract qth roots, then it will be inside the extended local ring. Okay, but on the other hand, this ring of qth power roots is a maximal subring in the field of fractions. Okay, so there must be a coincidence. So this maximal subring must just coincide with the local ring upstairs. Sorry, it should be big S and small s. Okay, but when we had this preparational lemma, maybe last Tuesday, it said that the local ring with its maximal ideal that is also uniquely defined uniquely determines the point. Okay, S prime is uniquely determined by its local ring inside K of SQ. Hence, S prime is uniquely determined and so the Frobenius is bijective. But now our topology, the risky topology, is a very stupid one. The closed subsets are just finite subsets, so certainly it's a homomorphism. Okay, so we proved the second part, right? Part B of lemma. We only have to compute its degree, and in the third part we have to prove that any inseparable morphism of degree Q is necessarily just the Frobenius morphism, nothing else, no other choices. Okay, so let's prove A. We take a parameter uniformizer pi at the point downstairs in the base, and then we know that when we extract Q's root of this, then it's a parameter upstairs at S prime, and this means that the pullback divisor is Q times S prime, but then we know that the total degree of this divisor is just the degree of the morphism. So the degree of our morphism Frobenius must be equal. Sorry, must be equal to Q. Okay, and now finally for C, let's consider any extension of any morphism say F from C to S, purely inseparable of degree Q, and then it means that the field extension is purely inseparable. C over K of S, again inseparable of degree Q, and in particular, it means that the Q's powers of the extension field, they lie inside the smaller field, the base field K of S, and then you can extract Q's powers, Q's roots, sorry, and they will contain the field of fractions on the covering curve, but the degree over K of S are both equal to Q, and hence this must be an equality. Okay, and so C is the normalization of S in the field of Q roots. Okay. So C equals SQ. Okay. So we classified all the inseparable morphisms between curves, and also explained that. So you see, these inseparable morphisms are ramified everywhere. Yeah, it's something counterintuitive. You do not encounter this in characteristic 0. Yeah, but in characteristic P, you can have a morphism that is homeomorphism at the level of points, but still is everywhere ramified. Something very strange. Okay, and so now let's start the next big topic, cohomology of coherent sheaves. And well, historically, one of the very first applications, or maybe reasons for developing of this abstract cohomology theory was the so-called Cousin problem for curves. And maybe everybody heard about this, but maybe I will review it. I don't know. What is there any opinion?
Скажите, пожалуйста.
Okay, so let me review just historic origin. For curves. So literally, this is the following question: given a finite collection of principal parts, like P1 at C1 and so on, Pn at Cn. So those are points of a projective smooth curve. And who are principal parts? The principal parts are Pi is you take a uniformizer pi I and write some polynomial in pi I inverse. So like a n pi I inverse to the power n plus a n minus 1 pi I to this power plus so on plus a1 pi I inverse like this. So given all this stuff, the question is if there is a global rational function on this curve, regular away from those marked points, and such that the principal part of f at ci equals pi. And the principal part is just modular regular function. F modular regular functions. So I mean, just if you want analytically, you can expand your function in a Laurent series around ci. Yeah, this will be an infinite series, but you are not interested in its Taylor part, the positive infinite series in positive powers of pi. You are only interested in the polar part. Okay, so you know that if your curve is P1, then this cosine problem always has a solution. So for P equals P1, the cosine problem always has a solution. And well, this is clear. Just you can construct this function as an explicit rational function. Yeah, for example, you can place all those points into finite part of P1, I mean, away from infinity. And you just add up those expressions, and there you are. So this is good, but the converse is also true. If the cosine problem always has a solution, then your curve must be isomorphic to projective line. And why this is so? The Xuanshine, can you tell why is it so? And sister, yes.
We can take one point and require only one pole at it and never else.
Right.
So
thank you. Yeah. So I guess you are not quite shy, but
yeah, I'm sorry.
the answer is correct. Thank you. Yeah. So take just n equals 1, and P1 is 1 over pi. So to say, and that we discussed this last time. Fine. So you see that this problem is non-trivial, and somehow the cohomology gives a well, somehow in industrial way to solve it. So still we will not have any cohomology today, but let me introduce it in a disguised form. So for arbitrary locally free sheaf F over C, so it's in place of the structure sheaf. So I somehow generalize this cosine problem for arbitrary locally free sheaf. We take this big constant quasi-coherent sheaf of rational sections. And or maybe just just take the vector space itself. over the field of rational functions on our curve. And inside this vector space of rational sections, we have just the stock of our locally free sheaf at some point in our curve. And we can take the quotient. And this is called the space of principal part of our sheaf at point C. So if F was the structure sheaf, as we discussed before, then the rational sections are just the field of rational functions, and this quotient K of C modulo the local ring is just the polynomials of the local uniformizer inverse. Okay, so that's exactly what we had as a definition of principal part at the previous page. Okay, so we have this, and maybe let's denote it as principal part at point C of our sheaf F. Okay, and then we somehow sheafify this. So we take a very stupid flabby sheaf, just like this. This is the direct sum over all points in our curve of those guys. So in other words, it's sectioned over some open set U. Is the direct sum over all points in this open set U of those principal parts at those points. Okay, this is the definition. Fine, and then we have an almost obvious lemma that there is a short exact sequence of sheaves on our curve C. So we have initial locally free sheaf F, then it embeds into the localization of its rational sections, and this thing projects onto the sheaf of principal parts.
Again, F is always locally free.
Oh yes, absolutely.
And we cannot define cohomology for non-locally free.
Well, today we will not pronounce this word cohomology, but we'll somehow get some formula for the first cohomology of a locally free sheaf.
Okay.
If it's non-locally free, then it's a direct sum of the locally free part and torsion part mapped by zero into this localization of rational sections. So, and it does not have first cohomology anyway, because it's flabby. Okay, so we have such a short exact sequence. Well, alpha is this morphism, and those two are flappy and quasi-coherent. Okay, so this we already know. I mean, localization of rational sections is defined as localization, and so it's quasi-coherent sheaf by construction. And the principal part is the direct sum of skyscrapers. So these are big skyscrapers. Usually we deal with finite dimensional K vector spaces. These are very big. They look not like fibers, but like stalks. But in this case, they're also fibers. Yeah, because you just take the direct sums of all such guys. There is no interaction between the different points C. You see? Okay, and maybe just there is essentially nothing to prove. Maybe just one comment. On how to define alpha. Well, of alpha. Well, you take a rational section. Let me call it F. A rational of F, and this is the same as a global section of this localization. Okay, and then you see it's almost everywhere regular. Okay, so F must be regular over an open subset, say V in C, and hence can have polar parts only at the complement. Okay, and this is a finite subset. And I mean, when I say that my sheaf is at the direct sum, then it means that any section must lie only infinitely many sums, right? Otherwise, I would say it's direct product. And this is what I'm explaining now, that actually this alpha lands in the direct sum. Alpha lands in the direct sum as opposed to the direct product. Okay, so alpha is well defined, and there we are. And well, maybe sorry, maybe I need to say one more word, that the exactness is checked at the level of stocks, and there it's evident. So we are really done. And
Да, почему ядро равно пучку F?
because the kernel is, consists of well, the local sections of the kernel are those sections of the are those rational sections that have no polar principal parts, right? And then by definition, they are exactly regular sections.
Спасибо.
So that's also clear. And now we can pass to the global sections. And we obtain a short exact, well, a very short exact sequence like this. Here just rational sections of F. Then there is the direct sum over all.
Раньше мы обозначили это пучком, а теперь это сечение.
So the sheaf is with tilde. Yeah, you have this quasi-coherent sheaf localization of this vector space, and the global sections is just this vector space itself. Okay.
А в чем разница обозначения пучка главных частей и сечения пучка главных частей?
Well, essentially, well, so this is the direct sum over all C, the principal parts at C of F. Well, it's essentially there is no difference because the sheaf was defined as this direct sum of its stocks, and the global sections are just this.
Просто совпадают.
So the local sections of this principal part sheaf are not this whole sum, but only over those points in the open set U. Okay, and now I take global sections. So I take direct sum over all points C in C. Okay. Okay, but at the level of global sections, this is not necessarily surjective. So the Cousin problem for our locally free sheaf F asks if alpha is surjective. Okay. So let's state the following obvious lemma, that alpha is surjective. So the Cousin problem has a solution if our curve C is affine. And the second part, well, already stated before that if C is projective, then alpha is surjective for the structure sheaf if our curve is the projective line. So B already proved, and A also already proved, but it was a long time ago, so maybe you forgot. So for affine varieties, algebraic varieties, the functor of global sections from quasi-coherent sheaves to modules over the ring of regular functions is an exact equivalence with length of categories. Okay. So there we are. Okay, so maybe again a piece of terminology. We say that F is acyclic if alpha is surjective. Okay, so if the cosine problem that does have a solution all for F. Okay, and now let's formulate a criterion. So F is acyclic if and only if for any effective divisor D on our curve C and any point on our curve. If we take the global sections of our sheaf twisted by D plus this point, and also global sections of F twisted just by D, then the dimension grows exactly by the rank of F. Okay, so if we allow just one more polar point, then the dimension of such well, rational sections grows exactly by the rank of F. Okay, so let's prove this. So we will start with an effective divisor. Divisor D, and then we take the sections with poles at this divisor and take the corresponding principal part. Then the dimension of this, I mean, this is a skyscraper, oh, no, not skyscraper, this is a torsion sheaf supported at, well, maybe let me rewrite this. So F of B modulo F is a torsion sheaf supported at our divisor, and dimension of its global sections modulo F equals the degree of this divisor times the rank of F. This we proved last time. Okay, but this thing lies in the principal parts of F. Okay, namely they are principal parts. Well, there are some principal parts supported at the divisor D. Okay, and if we intersect the image of alpha with this part of principal parts, then this intersection is just the quotient global sections of sections of F with poles in the divisor D modular regular sections. Okay, and so if F is acyclic, then well, maybe it's it's equivalent. So sorry, F is acyclic if the dimension of this quotient is just the degree of D times rank F. Okay, but this is true for any D, in particular for D prime, that is D plus 1.3. Okay, and hence this quotient, the dimension must jump exactly by the rank of, and that's it. Okay, that's it for today. I think for once I was not late, but let me say a word of apology for the next home assignment that I will distribute next Tuesday. There again, we will not mention cohomology, though we will start doing cohomology next Tuesday. And the sole purpose of this home assignment will be to show the how to say it, the unnatural difficulties you go into if you try to avoid cohomology. So when we developed cohomology theory, those exercises will become void, so to say. This will be absolutely evident. So if you choose not to submit them in time on deadline, then there will be nothing to submit, because with cohomology there will be nothing to prove. But if you try to do it without cohomology, this will be quite non-trivial. So this will be a challenge for good students who try to keep deadlines. Okay, so thanks for today. If there are no questions, I'm saving the notes, and I'm crossing my fingers that they are really saved this time. Okay, and I'm stopping.
Можно спросить по странице 3? Страница 3.
Yes, though. Okay, let me try to open it. But then, oops. Again, nothing. What happens? Nothing saved. Sorry. Again, nothing was saved. Why? No, nothing was saved at all. A disaster. I don't know why that happened. So there's no page 3.
Ну я тогда просто скажу словами.
Okay.
Мы там доказывали, ну, в общем, было такое обозначение введено, или не обозначение, но, в общем, было написано, что дивизор омега
No, it's in
фактор
Russian it's called
PS.
divisor. It's in Russian it is called divisor.
Извините.
Yes.
Дивизор омега
Yes.
c фактор PS равен сумме
Yes.
dc умножить на c. И в такой формулировке c я воспринимаю как подпучок дифференциалов. А потом мы написали, что вот это c маленькая – это точка на кривой. Почему это одно и то же?
Well,
Это же какой-то дифференциал все-таки.
well, I don't understand your question. I don't know what to say.
Что такое
You-
вот c в таком разложении? Дивизора.
Well, you have the one forms on the base curve S. You have its pullback to curve C. There is a morphism from here to OC, and it's an embedding of locally free rank 1 invertible sheaves, and in the quotient you have this relative differential like this. That's all. And also you can identify OC with the pullback of this guy twisted by the divisor associated to this torsion sheaf. And that's just by definition. There's a torsion sheaf.
Понятно, да. А когда мы стали раскладывать дивизор
If you have
омега,
arbitrary torsion,
простые,
arbitrary invertible sheaves like this, 0 to L prime to some torsion sheaf T, then always L prime is L twisted by the divisor associated to T. That's always true. There is nothing specific about differential forms. Okay.
наверное, просто там наложение обозначений произошло. Мы простой дивизор в разложении дивизора омега обозначили той же буквой, как и точку на кривой.
Well, this divisor is the sum over some points in C. C minus 1, C, something like this.
А вот это c маленькая, это точка на кривой.
Yes.
Но он же должен быть под пучком в омеге большом, то есть каким-то дифференциалом.
No. Why? No. I don't understand. There's a torsion sheaf, it's a quotient sheaf, but any torsion sheaf has associated divisor. This divisor is sum of points with multiplicities. That remember the sections of your torsion sheaf. That's it. Nothing else. The real problem I have is why my tablet does not save my notes anymore. If anybody has an idea, it will be very, very welcome. Otherwise, I don't know what to do.
Ну, именно почему не сохраняет, непонятно, но решить это можно, если выйдет видео, можно проскринить и PDF-ку собрать.
Okay, maybe if you can do this and send it to everybody, I'll be very much obliged to you.
Да, я могу, но для этого надо дождаться видео на канале.
Okay.
Professor, I have a question.
Yes.
So did you said you encourage us to solve without the shift cohomology for this homework?
I will send out the next home assignment next Tuesday, February 15th, and cohomology will not be mentioned in the formulations.
Yeah.
But if you use cohomology, then it'll be all trivial.
Yeah.
But without
I
use of cohomology, it will be quite non-trivial.
Yeah, I see. Because I thought it is strange because this homework doesn't have
Yeah.
to use. Yeah. Okay. Yeah.
Right.
Never mind.
Okay. So I'm stopping the recording.